Okay, welcome back. We're looking at another example of continuous time convolution here. Given an LTI system with input x of t and impulse response h of t, find the output. So first of all, let's explain what it is that we're trying to do. We have some system, like a circuit, that we know has the properties linearity and time invariance. Okay, we also know that we're going to be inputting e to the 2t u of t. So we're inputting this waveform. And we want to know when we, that might be a voltage or a current or something that we're putting into the circuit, if it's a circuit. And we want to know, what do we get out, right? Maybe we have some voltage across a capacitor, some current through an inductor, whatever. We want to know, what is the output? Okay, we also know that when we put in an impulse, we get out unit step of t minus 3. We get out this waveform because this is h. This is the impulse response. It is literally the response to an impulse. So given how the circuit behaves when you input an impulse, given that the circuit is linear and time invariant, let's find the output when the input is e to the 2t u of minus t. The answer requires no circuit analysis or any sort of mechanical analysis or whatever. The answer is that y is the convolution of x with h, and this is the mathematical definition of convolution. All right, so now let's get into the mathematical details. Tau here, I'm going to take the perspective that tau is the variable because I've got x of tau and I have h of, tau is there as well. So first thing I'm going to do is plot x of tau. So I'm just going to call this tau. Here's the origin. So if I replace t's with taus, this would be e to the 2 tau u of minus tau. So what does that look like? Well, this is a flipped unit step. This part of it is a flipped unit step. So flipped unit step is 1 over here in quadrant 2 and 0 over here in quadrant 1. Okay, and then e to the 2t, that's an exponential increase. So I have an exponential increase over here in quadrant 2, and then I have 0 over here. So that looks like this. Okay, this goes on forever. It never gets to 0. And then this is 0 over here. This is x of tau equals e to the 2 tau u of minus tau. Oh, that's not right. U of minus tau. Okay, and then right below that, I'm going to sketch h, or a flipped version of h. So here's tau again. Here's the origin. I'm going to try to line them up. Now, h is u of t minus 3, so that's a delayed unit step. So that the edge of the unit step where it transitions from 0 to 1 occurs at 3 units. So when I flip it, and I'm flipping it because this is h of minus tau. So when I flip it, that edge occurs at minus 3, and it goes from 1 to 0. So we'll call this minus 3. And this goes forever, this is 1, and then this goes on forever, that's 0. And so this is h of minus tau. All right, you should be pretty good with that. That's old stuff. Now, get my black. Okay. Now first, let's consider shifting h around by t, right? Because I don't have h of just minus tau, I have h of t minus tau. So we can look at this as a shift by t, right? All right, so notice if I shift by, let's say 0, t equals 0, so I don't shift at all. The non-zero overlap, I'll just write it out here until we see a pattern. Is between. So how do they line up? Well, I've got zeros here, so I have non-zero from minus infinity, right? Because both of these plots are non-zero at minus infinity all the way to minus 3. So tau is minus infinity and tau equals minus 3. All right, now if I shift by t equals 1, or whatever value of t you like, but I'll choose 1. So imagine this graph shifted to the right by 1 unit. Now I'd be going from minus infinity to minus 2. All right, and let's say, let's try a negative value of t. So if I shift this to the left by 1 unit, I'd put this edge at minus 4. So the non-zero overlap is all the way out here at minus infinity to now minus 4. Do we see a pattern, some relationship between the bounds and t? Keep that in mind. Now, let's try something. So there is a pattern there, but let's try what happens when I shift it by 4 units. So imagine now, if I shift this thing to the right by 4, that puts this edge at 1. I'm going to draw that in red. So I have something like this, putting that at 1 unit. Now where is the region of non-zero overlap? Well, it seems fixed. It's from minus infinity to 0, right? Because x is fixed. X is not being shifted. So no matter how much I shift h, I can't go further than 0 because this thing becomes 0 at 0. So in this case, I'd be integrating from tau equals minus infinity to tau equals 0. That seems to be a paradigm shift, a break in the pattern. See, because above this dashed line, we would be integrating from tau goes from minus infinity. And what's the pattern between t and tau? Well, it looks like it's t minus 3. Yeah. So notice if I plug in 0, t minus 3, so 0 minus 3, I would be integrating to minus 3. If I plug in 1, 1 minus 3 is minus 2, I'm integrating to minus 2. If I plug in minus 1, 1 minus 3 is minus 4. So that's the pattern. Tell me what t is. And that gives me the upper bound, t minus 3. And in all these situations, the lower bound is minus infinity. But see, t equals 4, when this leading edge goes past the origin, I have a paradigm shift. This pattern does not apply anymore. When t equals 4, I should be integrating from minus infinity to 0, not minus infinity to 1. So I'll have to handle below that dashed line separately. Okay, so that is all to say that this is going to apply for when t is less than 3. Right? Because if I shift this by 3, that puts it at the origin. And then anything more than that breaks the pattern. So for t less than 3, the output is the integral from minus infinity to t minus 3 of x of tau. So x of tau is e to the 2 tau. And I'm dropping the unit step, because the unit step is either 1 or 0, and we're talking about the non-zero part. So I'm just going to drop it, that's 1. Times h of t minus tau, but h is just a unit step. H is just 1 or 0. And so in the non-zero overlap, h is 1. And so this becomes my integral. Well, that's pretty simple, right? This is just 1 over 2 e to the 2 tau, plugging in minus infinity and t minus 3. Okay, so that's 1/2. When I plug in t minus 3, I get e to the 2 times t minus 3 minus, when I plug in minus infinity, e to the minus infinity is 0. So this is 1/2 e to the 2 t minus 3. And that's part of our answer. That applies only for when t is less than 3. Now, let's come back to our pattern. You see, when we already said when t is equal to 4, our non-zero overlap is between minus infinity and 0. And that's because x is fixed. We're not shifting x. And so even if we shift h by 5, that brings this over one more unit. But still, our non-zero overlap is between minus infinity and 0 because x is fixed. So in this regime, it doesn't matter how much we shift by, we're still going to be integrating from minus infinity to 0. So for t greater than or equal to 3, our output is found by integrating from negative infinity to 0. And then the integrand actually still stays the same because, again, the unit step is 1 in the non-zero part, and then we just have e to the 2 tau. Okay, so we can integrate that. That's 1/2 e to the 2 tau. We've got minus infinity to 0. So I plug in 0, e to the 0 is 1. And when I plug in minus infinity, e to the minus infinity is 0. So this is just a constant, interestingly. 1/2. So that's the other part of our answer. We have every value of t now covered. So our answer, written out, or combining the two parts, is 1/2 when t is greater than or equal to 3, and 1/2 e to the 2 t minus 3 when t is less than 3. That's the answer. Now I could have put the equals, here instead, because notice when t equals 3, for this expression, I get e to the 0 is 1, and then I have 1/2. So that is to say the output is continuous. So let's actually plot it. Here's t. This is going to be y of t. Okay, so for t less than 3, I have this thing, 1/2 e to the 2 times t minus 3. So that's going to look like this. Okay, and then at 3, this thing takes over. And so I just have a constant there, and that constant is at 1/2. But at 3, this is also equal to 1/2, so we have this continuity there. And that's the answer.